Okay, this is a quick video about the center of mass. I have a different video where I just show you how to calculate the center of mass, if that's all you're interested in. But this video is about why the center of mass is actually one of the most important concepts in physics. In order to understand center of mass, we have to take a look at these things as well. And so that's what we'll do. The first thing I'll say is when you first think of center of mass, you probably think, oh yeah, that's where I put the ruler so that it doesn't tip over, so that it does tip over. It is true that if you take some object and you balance it somewhere, if the center of mass is over the object, it will be stable. If the center of mass is over here, then perhaps the object will tip over. The thing is, this is absolutely not the center of mass. This is the center of gravity, which has to do with torque. On Earth, they are more or less the same thing, but conceptually, this is wrong. This is not what the center of mass is. I'll talk about center of gravity in a completely different video. The other thing you might think about center of mass is, I know what center of mass is. It's just the average location of where all the stuff is. And that is absolutely true. If you have a bunch of particles, you sum up over all those particles. If you have a continuous distribution, you do an integral instead of a sum. It's the same thing anyway. You can do it in 2 dimensions. You can do it in 1 dimension. There's all sorts of things you can do. The thing is that center of mass wasn't invented because people were interested in where the average location of all the mass is. I mean, it might be something you might be interested in, but that's not something that sounds super important, right? So what we want to do is try and understand, why is this a thing? Why is center of mass such a big deal? Okay, and the first thing we got to do is strip it down. We got to start much, much simpler. Okay, let's say you just have one point particle. Okay, and you put a force on that point particle. What does it do? It accelerates. Why? You're literally looking at Newton's second law. This is F equals ma. If you put a force on something, it accelerates. It's that simple. Okay? If you wait a short time, some time later, then because of that acceleration, you now have some speed. Delta V equals a times delta t. What physicists have done is we invented a name. We invented a name for something called impulse, which is if you exert a force on something for a certain amount of time, you are going to change the motion of that thing. And rather than talk about the acceleration, you can actually talk about the velocity instead. But it's not just the velocity. You've got this little m here too. And you might wonder, why do we need to talk about m times v? Isn't v sufficient? There's actually an advantage of talking about mv instead of v, and you probably already know that this is actually how momentum is defined. So impulse is really nothing more than change in momentum, and what we say is that the momentum of an object is the mass times its velocity at any given instant. Okay, that's the idea behind momentum. So we just define momentum that way. Okay, if all we had in the universe was one particle, there's really not much point in doing this. On the other hand, let's say that we have 2 particles, and let's say that these 2 particles exert forces on each other. Now, this is important. If they exert forces on each other, there's an F12 on the left and an F21 on the right, and by Newton's third law, those are equal and opposite. And so what does that mean? That means that the red guy experiences a velocity v1 after some time t, and the blue guy experiences a velocity t2 after some time t. But if you crunch the numbers and you do the math, the impulse this guy experiences is due to f12. The impulse that this guy experiences is due to f21. This is the change in momentum of 2 and the change in momentum of 1, but we just got done saying, because of Newton's third law, that that's actually the same thing. This is the same impulse on both. What does that mean? That means that delta P1 equals minus delta P2. Why the minus sign? Well, that's just directional. That's all that means. Pluses and minuses in physics are for direction. So that means, bizarrely, that if you add these 2 things together, delta P1 plus delta P2, they equal 0. And I want to point something out. If I add them together, what I'm kind of doing is finding the change in momentum of the entire system. What do you mean system? Well, in this case, my system is both particles, and apparently it's a thing that if I add up the momentum, it can't change. The momentum can't change. I add up all the forces acting on the system, I find that they add up to 0, and the consequence of that is that there is a conserved quantity. The particles move in opposite directions, and the reason they move in opposite directions is because they have to conserve momentum. This is an entirely different way of talking about physics. Understand that I'm using Newton's second law up here. Understand that down here, I am recasting the same behavior in an entirely different law. I'm not saying that they move in opposite directions because of Newton's third law and one gets pushed one way and one gets pushed the other way. I'm saying that because there are no external forces acting on my system, this quantity has to be conserved. And that means that if one goes to the right, in order to make it add up to zero, the other one needs to go to the left. This is an entirely different way of describing the exact same physics. The question is, though, what is conserved? Where is the system? Right? Where is the system? And what do I point at to show what's conserved? And so in this case, the sum of the forces on the system is the mass times the acceleration of the system. So in other words, it's Newton's second law on the system. That equals zero. But like, where do I point to see the system? So here's two objects, okay? These two objects, again, exert equal and opposite forces. And if I sum the forces on the system, I get Newton's second law on the system. If I solve for the acceleration of the system, I end up with this curious combination of things. That means that the position of the system has to be defined like this. If this looks familiar, it's because this is the first thing I showed you at the beginning of the video, how you've seen center of mass defined before. We're not interested in the average location of where all the mass is. We're interested in where the position of our system is so that we may apply Newton's second law to our system. This is called center of mass, and its value in physics is being able to use Newton's second law. Let's just say that one of the particles was a little bigger. This is an average, and if I calculate the average will move toward the red one. What if the blue one was bigger? Okay, it'll move that way. So this is still an average, but I'm not really interested in it as an average. I'm interested in it as the thing that is the system that is going to move. So in this particular case, let's just say, I don't know, the blue ball is bigger, so it doesn't move as far. Notice the only way that the average location of the system can't change is if this guy moves faster than this guy. Why? Because this guy has more mass. If this guy has more mass, the average should veer toward him. But if this guy is moving faster, it gets farther away, and that will prevent the average from moving along with this guy. So in this case, we say that the sum of the forces on the system are zero. The thing that's conserved is the position of the center of mass of the system. This purple guy does not move. Okay, here's the thing. What happens if the sum of the forces acting on this isn't zero? So more interesting behavior, right? This is great when momentum's conserved. What if momentum isn't conserved? Is all of this garbage? No. I want to pitch you something. Let's say you have a rod and you exert some external force on the rod. Notice I don't have canceling forces in this case. This is an unbalanced object. If I add the forces acting on this, they won't add up to zero. Here's the center of mass of the object. It's in the center. Let's just say that it's uniform, and we know that, look, it's an average, and so the average is right in the center, right? Okay. The thing is that when you push on this object, you have to push on it in a particular place, and there is a slice of mass at that particular place. That's the thing you're pushing. You're not pushing the rod. There is no rod. You push the piece of the rod that you touch, right? So when you do this, what happens? That piece goes flying off on its own and the rod stays where it is. Absolutely not. This piece is rigidly connected to the two pieces next to it. That means that there are some weird internal forces that we don't know anything about, but presumably are quite complicated. So what happens is when I push this guy, he tries to move up, but then these guys yank him back down. Now, of course, if they yank him back down, he's going to yank them back up. That is Newton's third law. If any force between two things has to be canceled. So these are action-reaction pairs, right? And if you think about it, if these guys start moving, you actually just started a whole chain of events where every single slice of this thing is going to feel some weird force. And now bear in mind, I'm not saying that the force is the same on every one of these slices. I'm saying that between each pair of slices, there are equal and opposite forces, and those forces are completely different for every single slice. If this sounds crazy, it's because it is. How on earth are we supposed to start to describe the motion of something if we don't know all of the forces acting on every single piece of it? The answer is you can't if you don't know the center of mass. So what we do is this. We say that the force acting on each slice is F sub I. And what I mean here when I say F sub I, what I really mean is the net force. In other words, I understand that there's this big force acting on it, but then there's all these weird internal forces as well. You need to know all the internal forces in order to find the net force on I. On the other hand, if you add up all the forces on the system, you add up all the forces on this guy plus all the forces on this guy plus all the forces plus all the forces on every single one of them, just like we did with the particles before, an amazing thing happens. You find out that they all sum just to this one external force. Why is that? That is because if you add the forces acting on this guy, for example, you will have the force of this guy pulling to the left. But when you add the force of this guy, you'll have an equal and opposite force acting to the right. In other words, all of these action-reaction pairs cancel. And so long as you are willing to look at the force on the system rather than the force on the slice, the only thing that matters are external forces. In other words, if we're willing to talk about the motion of the system, we don't need to know anything about intermolecular bonds or however what crazy spring Young modulus stuff is going on inside. We just need to know how hard you're pushing on it. We can say that the acceleration of the center of mass is this force acting on the system. So what does that mean? If I make a little dot that shows the center of mass and I say, all right, I push on this end of the rod, what do you expect the rod to do? Well, of course you know what it's going to do. It's going to tip upward. This end is going to go higher. And yet, what I'm telling you is, it's not only that end can go higher. The center of mass also has to move up. And the center of mass has to move up in a straight line. How do I know the center of mass has to move up in a straight line? Because the force pointed straight up. And F equals ma times cm. In other words, if I look at pieces of the rod, they engage in this weird kind of curly behavior. On the other hand, if I just stare at the center of mass on the rod, it's just like a point particle. The whole point of this is that if you're willing to find the center of mass of an object, you can use the techniques you used on point particles on extended objects. That is pretty amazing. The center of mass is the thing that obeys Newton's second law, and I ought to write like a point particle. When objects didn't have pieces, you didn't have to worry about this. Newton's second law works for point particles, but when objects have extent, you can still use Newton's second law so long as you treat the entire system like a point particle. I just want to show you a movie just to kind of highlight this. This is a box and it's filled with a bunch of balls, and the balls move around crazily, and I just want you to watch and see if this looks familiar. The balls are moving crazy, the box is moving crazy. The box is moving crazy, and yet, I don't know. So this is the center of mass I'm tracking on the inside. This is pretty amazing. I want to make something clear. I did not design this trajectory. I simply told the box, each piece of the box, to be in a uniform gravitational field. In other words, if you just take a box and you throw it, what does it do? It makes a little parabola. And what I'm telling you is I didn't tell these objects to make a parabola. Each object is doing its own thing. Each object is feeling gravity, but each object is also feeling all these crazy internal forces banging around inside the box. The net result of all of it is that the center of mass of the box, which isn't even a piece of anything, has to do what Newton's second law says a point particle would do. In case you think this is crazy, every single box you've ever picked up your entire life is filled with balls. It's filled with tons and tons and tons of gas molecules moving 500 meters a second, doing exactly what this box is doing, and you've never noticed this weird jittery behavior. But that weird jittery behavior is there. The average of all the mass is what you're seeing. That is the thing. This is pretty amazing because if you think about it, think about something as simple as a fish in the ocean. You might think that because a fish has lots of different pieces, in order to understand whether or not the fish will be buoyant, you'd need to know how the different pieces of the fish interact with each other. But the center of mass saves us from having to do that. The center of mass just says, look, what are the external forces? There's a buoyant force and there's gravity. If those are balanced, the fish float. So this tells us that Newton's third law makes the world possible to understand. Why? Because all these little internal forces cancel, and it's only because those internal forces cancel that we're able to predict the motion of anything at all. This is what we mean when we say momentum is conserved, And this is why the center of mass is such an important concept in physics. Okay, hopefully this video was more helpful than confusing.